Hi everyone. Because of the importance of exoplanetary atmospheric studies, I wanted here to show you our last development on the global climate model named LMDZ generic, and in particular in the chemical network and photochemistry part. The way we wanted to develop this model was to be flexible, to be able to simulate atmosphere of the different kind of exoplanets we can encounter. So the model we are using is the LMDZ generic, and the way I like to split this model is on three parts, considering the dynamical core, the physics part where more or less all the radiative transfer processes are done, and the last part where we will focus on the chemical module. And our goal was to make it really flexible to simulate different kind of exoplanets. And for that, the first step was to think about the input chemical network. And we have two issues. The way you input the network. So we decided to choose as much flexible as it can be, a format as much flexible as it can be, and that a format that could be derived from any database with a simple code. You can just download the input files from the from output of database, and with simple codes get the right format. And the real first issue was to implement a generic formula, as generic as possible, for the kinetic coefficient rates. And for that, we based our formula on Arrhenius law and a strip body reaction rates. But of course, this formula could be really updated easily. And if you want, you can just modify this formula to be more generic. But for now, it's really something like it's generic enough. Um, the second issue was more linked to the photolysis process. We we know that the radiative transfer is done on more the visible and the infrared parts. But for the photochemical process, we needed to extend and to have a calculation on the UV part. The way it was done before was with pre-calculated tables, which were interpolated into the code. But to be flexible, we needed something you can easily switch and added new photolysis reaction, like only on the inputs file. And for that, we decided to implement a non-line calculation of the photolysis. That was the first step. And considering those photolysis, the consequences of that is like a hit, a hit, a hit would need to be consistent with the radiative transfer which was done. For if there is no overlap of the wavelengths for the calculation, it's not a problem. We just implemented on the photolysis online, photolysis heating also online. But when we got to the example of the ozone, we saw that considering the visible absorption of ozone was really important, and this means that we have an overlap on the photolysis calculation model in the radiative transfer part, and so we need to couple that correctly. And for that, we decided to stop. Well, it's adjustable. You can do whatever you want. It's just a value, but you we decide you. This is a parameter where we can stop the calculation of the photolysis heating at the age, for example, at the radiative transfer. And for the heating calculation, we need to, of the photolysis, we need to consider it on the radiative transfer part. And for that, we also implemented a calculation of the correlated K for the calculation of the radiative transfer online. A mix of some species you decided to mix online with the correlated K you have. And for us, for example, we decided to mix the ozone, um, to mix the ozone corrected K with the corrected K we have. Like that, we get a perfect coupling between the heat of ozone on the photolysis UV part and on the visible part, thanks to our mix on the corrected K. So it's really a very important thing to be careful of the coupling of the photolysis processes with the physical parts. And also, it's what we have done for now, but we still have like a process, a heating process to consider, and it's the reaction that could be involved in the heating process or cooling process for the temperature dependency, because some reaction have also an impact on the temperature, and we still have not implemented that, but it could be really important and significant, especially for hot planets. So it's kind of the new step I wanted also to highlight. But for now, for the model we have, we tested on Earth, and what we have is pretty good. We have the ozone layer here compared to reference from Brasser and Goldblatt paper, and what we can see is like the heat due to the photolysis of ozone is seeable on the temperature profile. You have this heat, and it's giving like pretty correct results. But now, what we want is to be able to use on exoplanets. So let's go and let's see the Trappist case, and in particular the one I like, Trappist-1e case, because why it's interesting, and for me in particular it's interesting because considering the flux received at the top of the atmosphere for the ozone processes. And why here we can see in green the flux received by Earth from the sun, and in blue the flux received by Trappist-1e by its star. And we know that at the red dwarf we receive more flux on UV than in visible compared to the sun. And in particular in Trappist-1e we have this balance at 200 nanometers, where compared to Earth, the Trappist-1e receives more flux in UV under 200 nanometer and less flux after up to 200 nanometers. And this is a particular case for me, because if you considering the photolysis these processes, so we are looking at the cross sections, we can see that to get those photolysis processes, the cross section of the species is more or less all under 200 nanometers. So the photolysis are done under 200 nanometers, except the ozone photodissociation, which is done up to 200 nanometers. So in particular, we can notice that the oxygen O2 photodissociation is done under 200 nanometers, and the ozone photodissociation is done up to 200 nanometers. That means, considering the Chapman cycle, that we produce more ozone and we destroy less ozone compared to what is done on Earth. So if we take a Earth atmosphere and we put it on Trappist-1e, what we get is like a sustainable ozone layer. So it means like on those planets, you could find a sustainable, you could have a sustainable ozone layer. It's possible. And this is a simulation we've done on considering TRAPPIST-1e planets, and it's what we get. So and why having a sustainable ozone layer it's interesting. It's because as on Earth, this ozone layer protects the surface from UV radiation. And here what we can see, this is um, the flux received in TRAPPIST-1e, and what we can see is like the top of the atmosphere flux does not reach the surface. So this is really, really, really interesting to have this kind of sustainable ozone layer on exoplanets. And so finally, what I wanted really to highlight is like we have this flexible chemical module to have like a different kind of network. You can input really easily, switch from one to another, and with important coupling heating, because we know that heating of the chemistry and photochemistry could be really important on exoplanet's atmosphere. It could change everything, as for example the Titan atmosphere and such like that. So now just have to need further development, as I exposed, and further explain application. So thank you very much.